So for this first one, we want to see what the graph tells us about what's happening here. Now, one of the things that I hope you notice is that basically there's three pieces to it. And we just have to figure out what's happening in each of these three phases separately. So let's start with between 0 and 2. Obviously the graph is increasing there. What does that tell us about this situation? This is some object moving. We can know that much. How's it moving between 0 and 2? So some people are talking about how between 0 and 2 it's at a constant rate, or it's accelerating. Well, those are different ideas right in those two. So let's start by focusing there. Does it look like the speed is changing here?
Yes.
No.
Well, let's look at it this way. Let's go between here, between 0 and 1. How far up did it go during that time period? 2, okay. Between the next point here, in the next second, how far up did it go? 2. So this advanced, because notice this is a displacement graph, notice that it advanced by 2 meters every second.
Oh.
Is the speed changing?
No.
No. That's a constant speed then. So then during this first part, we have some constant speed. So then what's happening then between 2 and 7? So between 2 and 7, there's two main ideas that come out. One idea is it's moving at a steady rate. The other option is it's not moving at all. Well, this is talking about displacement, right? At the start of that time period, it's at 4 meters. At the end of that time period, it's at 4 meters. It didn't change at all, right? Nope. So when it's flat like this, that means it's not changing at all. Basically, it's not moving. All right, so then what about between 7 and 8? Obviously, it's changing where it is. But what is different between these two sections?
It's going back to
So does this mean then that we changed direction, or we changed how the speed has been changed? Like, does this mean that we're slowing down?
No.
Or does it mean that we changed direction?
Change direction.
Yeah. It does mean change direction, because this is a displacement graph. In other words, it's a graph showing how far away is this object from some starting point, wherever 0, 0 was defined to be. How far is it from there over time? So as you take a look at that second part, actually third part here, between 7 and 8, what it's telling us is that the object is moving back toward where it started from. So it's coming back closer. Now, we could also get into slope, and we could see, oh, well, and it's coming back faster than it went out, and a few little things like that dealing with slope. But we don't even need to get into some of that detail. Now, that's because this is a displacement graph. What I'd like you now to do is sketch what the derivative of this function would look like, and then we're going to talk about the meaning of that derivative.
No.
All right, so I'm going to go ahead and start sketching this. Now, when I go to sketch this, the first thing that I need to know is, what's the derivative function mean? Remember our definition of derivative. Derivative tells us the slope of the tangent line at a point. Well, this is all straight. Therefore, it's just the slope of that section of the line. So, what's the slope between 0 and 2? The slope is 2. What is the slope between 2 and 7? 0. What is the slope between 7 and 8?
-4.
-8.
Wait, hold up. What?
Sorry, yes, that is -4.
Woo!
For some reason, I thought it was up at 8 instead of up at 4. All right. And so we got our slope of 2, 0, -4. Now, if I want to then turn that into a graph, that means then that my first slope between 0 and 2, that's going to be up here at 2. But notice it's a constant slope there. It is 2 all the way between 0 and 2. Then between 2 and 7, it's at 0. Okay, but then between 7 and 8, we found out it was -4. So it's going to be down here. Now that's our starting graph, but it's not actually going to be our final result, because we have to deal with the question now. How should we end each of these segments? Should these be open circles or closed circles, or one of each? Well, that comes back again to the idea about the derivative, because the derivative is the slope of the tangent line at a point. Now, at 2 here, how would we find the slope of that tangent line? Because the tangent, it could mean a few different things. It could be the tangent to the line coming in, or it could be the tangent to the line coming out, or it could be the tangent that's just touching that one point and only that one point, but there's lots of ways we could do that. So it's hard to say exactly what that slope would be. In fact, it's so hard that we can't. There is no derivative at a corner of the graph like that, because the limit from the left is different from the limit from the right. And so then we end up with open circles on the ends of both of those. The same thing is going to happen over here at 7, where I'm going to have an open circle and an open circle. Now the last question then is, what does this graph actually represent? So like, I still have time on my x-axis, on my horizontal axis here. What would the vertical axis be labeled? Well, the first one was displacement up there. If I took, it's lagging again. If I took displacement and I find the derivative is slope, right? So it's the change in displacement over the change in time. What's displacement over time mean?
Meters.
Well, that's like position over time, or distance over time. That's like speed. And so we might label that then as speed, or velocity.
Well, it does look like a velocity graph.
Now, there's actually a difference between those two concepts, which we haven't looked at yet. Technically, yeah, it's velocity. But we haven't gotten into those details. The idea of seeing that we can know what it is because we're changing the displacement in regards to time. So it's a displacement over time. You could even put in the delta if you like to be fancy there. Delta displacement over delta time. And that's how we know it's velocity. Now, in that problem, we saw that at a corner of a graph, that there was no derivative. And so, there's no derivative at a corner, there's no derivative at a discontinuity, and there's no derivative if there's a vertical tangent. Now, vertical tangent, we haven't seen that come up very often, but it does happen here and there. All these are cases where the derivative does not exist. We reference that as saying that the function is not differentiable. Basically, when we say differentiable, we mean we can take the derivative. So a little bit of vocabulary there, worth adding into your notes, just so we remember the vocabulary as we talk about these things. So here's our answers for those first three. Remember to include the open circles at the ends there. Now, I didn't put any open circles at the ends over here. You certainly can, but I wouldn't consider that required because we aren't told what's actually happening if this graph is supposed to be continuing or if it actually just ends at that point. On the back side, though, these three are particularly interesting because these three graphs, they all look very different. You notice, like this one's starting up in the positives. This one's starting at 0. This one starts positive but then goes negative. But all of them have very similar graphs. It's just a matter of how steep it is. Because remember, our derivative graph is just a graph of the slope. So all I care about is the slope. I could move this line, I could slide it up and down as much as I want to, but as long as the slope doesn't change, the graph of the derivative also will not change. And then our last set of answers there. And again, just looking at little details, basically it's about is the slope positive, negative, and then how positive or how negative along the way. All right, so for this problem then, we have some manufacturer producing bolts of fabric. The cost of producing X yards of the fabric is represented as C. C is the F of X. All right. What is the meaning of the derivative? That is, the meaning of F prime of X. What would the derivative really mean here?
F of C equals X.
Well, remember how I represented it in the graph? We could talk about like slope coming back to delta y over delta x. We could do the same kind of thing here. So it'd be delta c over delta x, in this case because we're actually calling it x yards of fabric. And so what does c represent again? Cost. So I could read this then as cost. It's dividing, so that's like per.
Oh,
Cost per, what does x represent? Yard.
Unit price.
So the derivative then represents the cost per yard. And then that then tells us how we can know the units, because cost is measured in dollars, and yards are measured in, well, yards. So it's dollars per yard. Or we could represent it as dollars per yard, that sort of a thing. Something like that. Right, now, knowing that then, how could we then make sense out of this statement right here? F prime of 1,000 equals 9. What's that really mean? All right, so as you look at this, again, think about what each variable means and where each variable goes. The 1,000 in here, what variable is that?
X, which is yards.
That's x, yeah. So that's the number of yards. So basically it's saying for 1,000 yards. Okay. Then we got to figure out what follows that. All right, so then what does the 9 represent? Remember, the 9 is f prime of x. So that was our cost per yard.
Oh.
And so for 1,000 yards, the cost is $9 per yard. Now, we can even actually say this a little bit better than that, though, because that was just kind of a way to make sense of it. Specifically, rather than for 1,000 yards, it actually is saying the 1,000th yard of fabric would cost us $9 a yard to make. Because obviously it could be changing, right? The first yard of fabric could cost very different from the 1,000th yard of fabric. We don't know that this is a constant relationship. In fact, which do you think would be greater? F prime of 50 or F prime of 500?
F of 50.
Yeah, I would definitely agree. I think that
Look at Costco.
at F prime of 50, the cost per bolt, or the cost per yard for 50 is going to be more than the cost per yard at 500. Because, one, we're buying more material, so we can be buying in bulk. Also, if we're actually producing this stuff, there's usually a bunch of upfront costs, like you got to get the machinery, and you got to hire the employees, you got to get the space to be making the stuff in.
Labor's the most.
So you got a lot of upfront things where that first yard, oh, it's costing you a ton just to get up and running. But by the time you're making 500 or even 5,000, it's costing you a lot less per yard because now you're distributing those upfront costs across the whole thing. So those all ends up coming into it. So much bigger? Yeah, I'd definitely expect the 50 to be a higher cost than some of the other ones.